Let's take a look at this bond valuation and interest rate risk problem. It's problem 5-9. I'll read it to you. The Garrity Company has two bond issues outstanding. Both bonds pay $100 annual interest plus $1,000 at maturity. Bond L has a maturity of 15 years and bond S has a maturity of 1 year. L stands for long, S stands for short. Okay, part A says, what will be the value of each of these bonds when the going rate of interest is 5%, 8%, and 12%. Assume that there is only one more interest payment to be made on bond S. We'll tackle part B in a moment. Alright, I've staged the problem in front of you, and we see that bond maturity of L is 15 and S is 1. So those are the number of periods, and let me bring that color to light here. If I can click on the right shading, then I'd be just fine. Okay, so the interest then is 5% for part 1, A1. The future value of both bonds is $1,000, and they tell us that the payment is $100. So what we've got to do is solve for the present value. And what I'll do is, I have the answer here, but what I want to do is call this up by hitting the formula bar, and then I'll show you where we fit this in. Let me just put it here. So the rate was given in cell C14, which was 5%. C13 was the 15-year number of periods. Payment C16, $100. Future value, $1,000. We don't need to worry about type. We assume the payment occurs at the end. You could put in a 0, or you can just leave it blank, which is what I usually do. And when I hit that, you can see the formula all comes together, and I get 1518 times 98. Now, it turns out to be negative because, keep in mind, Excel assumes that any outflow of payments are negative and inflow are positive, and if you were receiving $1,000 at the end and $100 each period, then you must have given up equivalent value of 1518.98. So to switch that, all you've got to do is put a negative in front of the formula. That's one way. Okay. You could also have changed the 100 and 1,000 to negative, and you'd have an answer coming back to you as a positive number. And if I copy that over here to bond S, I get 1047.60. Okay. So what does that tell us? We've got a higher present value on the long-term bond than the short-term bond. Well, what happens at 8%? So all I've got to do now is change the 8%. This is part 2, right? Everything else remains the same. And the 1518 becomes 1711. And the 1047 right there, when I hit 8%, we'll see the change, becomes 108. So we see a decrease in the dollar amount of the change. When I do it at 12%, we should see that those numbers go down even more. Yep, 863, and then down to 982. Okay? So then, the next thing we need to solve is part B, which says, why does the longer-term 15-year bond fluctuate more when interest rates change than does the shorter bond? And to show the fluctuation again, I want to show 5% was 1518. Okay? And if I show 12%, we drop to 863. So that's a pretty, substantial change, right? $863 versus $1,500 in round terms. We'll do the same thing for the short bond. 1047 versus 982. So the fluctuation isn't nearly as great. And to answer that, I think the best thing I can do is just show you how the author explained it. So let me move that over, and I'll read that to you. Put this right here. Okay. So what the author says is, think about a bond that matures in 1 month. Its present value is influenced primarily by the maturity value, which will be received in only 1 month. Even if interest rates double, the price of the bond will still be close to $1,000. A 1-year bond's value would fluctuate more than a 1-month bond's value because of the difference in the timing of receipts. However, its value would still be fairly close to the 1,000, the face value, even if interest rates doubled. But a long-term bond paying semi-annual coupons, meaning it pays interest twice a year, on the other hand, will be dominated by distant receipts. So the value of that bond is impacted by all of those receipts that are going to take place over, many periods. And then they're multiplied by the present value formula, which is 1 divided by 1 plus the discount rate divided by 2 raised to the power of t. And if the required rate increases, these multipliers will decrease significantly. So if you work through the math, you'll see how that works. Another way to view this problem is from an opportunity point of view. A 1-month bond can be reinvested at the new rate very quickly, and hence the opportunity to invest at this new rate is now lost. However, a long-term bond locks in subnormal returns for a long period of time. What this tells us is reinvestment risk is significant on longer-term instruments.